Hi students. So today we start optimization tutorial 3. Today I'm going to talk about optimality criteria. I am Dr. Ganguly. Now in today's lecture or tutorial I'm going to cover several things. For example, necessary and sufficient conditions for optimization, the minimum point of functions of single variables and two variables, multivariables, the KKT conditions in optimization. These are often known as the optimality criteria for constraint optimization problem. And we are also going to look at examples on how to find the minimum point of functions with equality constraints and for functions with inequality constraints. So of course today's video is a tutorial. It only contains solved examples. If you are interested in the lecture and the theory, you should look at my optimization lecture 3, optimality criteria, and that's going to give you the theory about the necessary and sufficient conditions, the KKT conditions, and so on. I'm going to leave a link to that particular lecture in the description box and also on the end screen. So let's start with some very simple problems to warm up, and then we will proceed to more complex problems. So the first problem is find the minimum point of this function f of x is x square minus 2x plus 10. Now, of course, you know this is a problem which you could solve from high school calculus, and you may have done these types of problems before. So essentially, if you have a function like this, what happens is that you can take its derivative and set it equal to 0, and that's going to give you the stationary points or the critical points of this particular function. So in this case, what happens if we take the derivative, we get 2x minus 2 equal to 0. And so I get the solution x star is 1. This is a stationary point. Now the stationary point could be a minimum point, it could be a maximum point, it could be a saddle point. And so what we need to do is we need to look at the sufficient condition, and that involves finding the second derivative. So the first derivative is the necessary condition for a point to be minimum, and the second condition, which is that the second derivative should be positive or should be greater than 0, that's the sufficient condition. So in this simple function, we see that the second derivative is simply going to be equal to 2, and therefore the second derivative is greater than 0. So this point x star is 1 corresponds to a minimum point. Now at some places in this video I'm going to talk about x star. That's simply a way to say that's a stationary point or a minimum point, and someplace I may skip it also once you get the hang of the fact that we are dealing with the optimization problems here. Now let's move to question number 2, which asks you to find the minimum points of the function sin x. Now this is a function which is interesting, pretty much popular and ubiquitous as far as math is concerned. And the interesting thing here is that if you take the derivative and set it to 0, you will be setting cos x equal to 0, and this has got a multiplicity of solutions. So this is something which is sometimes known as a multimodal optimization problem. There are going to be an infinite number of stationary points here. So these stationary points, for example, correspond to plus and minus pi by 2, plus and minus 3 pi by 2, plus and minus 5 pi by 2, and so on. So at all these stationary points, the derivative of f of x, which is cos x, becomes 0. So these are essentially the roots of cos x. Now for finding out what are the minimum points, I need to take the second derivative. So in this case, the second derivative becomes minus sin x. So the derivative of cos x is minus sin x, and this should be greater than 0. Now if I look at all these stationary points, there are only a subset of points at which the condition is satisfied that the second derivative is greater than 0, and these points are minus pi by 2, 3 pi by 2, minus 5 by pi by 2, 7 pi by 2, minus 9 pi by 2, and so on. So again, this is a continuing series. You can put some dots here to make that clear. So here we see that the necessary condition is this here, which gives us stationary points, and the sufficient condition is the second derivative condition, which gives us the minimum points of this function. Now you can of course graph sine of x, and you can verify this information here. Let's come to question number 3, which is find the minimum point of this function f of x is x square plus e to the power minus x. So immediately I can take this function, I can differentiate it. So the derivative is going to be 2x minus e to the power minus x, and I can set this to 0. So once I have this derivative here, I can try to rewrite this and solve this system. Now this looks like a typical nonlinear equation, a transcendental equation, and many people resort to Newton-Raphson and so on to solve this kind of nonlinear equation. But let's see if there is an exact solution to this problem. So I can write this particular equation as e to the power minus x equals 2x, and then I can write it as 1 equals 2x e to the power x, which I can then finally write as x ex is half. Now once I get this form, I can use the fact that there is something known as the Lambert W function. And what happens is that if we apply the Lambert W function to some function, for example a e to the power a, then I get a. So that is the thing which the Lambert W function does on any function of this type. And here I see that this x e to the power x is in the form a e to the power a. So I can apply the Lambert W function to both sides of this equation, and then I get w x e x is w half. So once I get this, I can find the solution, because what will happen is that this term involving w x e x will simply become x from the definition of the Lambert W function itself. And then what happens is that I can find x as w half, and the Lambert W function for half is going to be 0.351734. Now how did I find this function? I'm going to show you this in the next slide. So what I do is I go to Wolfram Alpha. This is a website, a software package, or I should say an online system. And here if I type in Lambert W half, I get the value here to a huge number of decimal places. Now I am not interested in all these decimal places, so I can take x is w half is 0.351734, which you can see are the first 5 terms after the decimal point in the Lambert W function value at half. So this is a function which is defined for typical values. You remember functions such as the Bessel function, the gamma function, and so on. So you can start thinking of the Lambert W function in the same manner. So now that we know the minimum point, or I should say the stationary point, we can check whether that is the minimum point. So in fact, we saw that x is w half, that was 0.351734, that was the stationary point. So I take the second derivative of this function, x square plus e minus x. Remember, the first derivative was 2x minus e to the power minus x. So the second derivative is going to be 2 plus e to the power minus x. I then substitute this value of x in this particular function, and so I get 2.7034, which of course is greater than 0. Therefore the second derivative is greater than 0. That is of course the criteria for a minimum point. So we have found the minimum point of this particular function x square plus e to the power minus x. Now we are going to use this type of function repeatedly in this course in further dimensions beyond 1 also, to check out different algorithms. So this is something to keep in mind. Now let's try to slightly complicate our life by looking at this two-dimensional function, and this is a very simple two-dimensional function. Fx is x1 square plus 2x2 square. Now I'm just keeping this x notation here, I'm not putting any bold here. So I hope you understand that in all these cases this is simply a multi-dimensional or multivariate function. So now I have to find the minimum points of this function, so let's try to do that. Now to do that, I need to calculate two things. One is the gradient vector and one is the Hessian matrix. So again, to calculate the gradient vector, what I need to do is I need to take the partial derivatives of the function. So df by dx1 is 2x1, df by dx2 is 4x2, and then I can write the gradient vector. So the first term in the gradient vector is the first partial derivative with respect to x1. The second term is the partial derivative with respect to x2, and then I need to set this gradient vector to 0. So this is the necessary condition for stationary point for a multivariate function, that the gradient should be 0. Now once I set the gradient to 0 in this simple problem, I get x1 is 0, x2 is 0, and this particular setup in green is the stationary point for this function. Now we need to figure out whether this is a minimum point, a maximum point, or a saddle point, and for that I can need to calculate the Hessian matrix. So H is 2 0 0 4. Remember, this is the matrix of the second partial derivative. So in this case I have to take d2f by dx1 square, that's going to give me 2, and d2f by dx2 square, that's going to give me 4, and the term d2f by dx1 dx2, that's 0, and d2f by dx2 dx1 is also 0. So I get the H matrix here. I can immediately find the eigenvalues of this matrix. They come out to 2 and 4. So this is a positive definite matrix, and therefore this particular point x1 0 x2 0, this is a minimum point. So the sufficient condition for a multivariate condition function is that the Hessian should be positive definite, and that's something which we have obtained here. Now let's come to question number 5, and that is find the stationary points of this function. F of x is x1 square plus 2x2 square plus e to the power minus x1 minus x2. Now if you have been following my tutorials, you know that this is a function I like. In fact, this is the function I proposed for the first time in my book, and in fact this function is very useful for optimization. So let us try to look at this function and find its stationary point. So to find the stationary point, I immediately set the gradient to 0 or the gradient to 0. So to set the gradient to 0, I need to calculate the partial derivative. So with respect to x1, I get 2x1 minus e to the power minus x1 minus x2 from here, and df by dx2 is going to be 4x2 minus e to the power minus x1 minus x2. So I put this here. Remember, c is the gradient vector, and I set this equal to 0. So that gives me these two equations. So these are nonlinear equations we need to solve. Now even before we solve it, just looking at these two equations, if we were to subtract these two equations, we would get something like 2x1 minus 4x2 equal to 0, or x1 would be equal to 2x2. So that's the first equation which I get, which tells me that if I were to obtain x2, for example, I would know x1, or if I were to obtain x1, I would know x2. So one equation is very helpful here. Now what we do, we take this equation and we substitute this in one of the equations here. So let's substitute this in the first equation. So I get 2 into 2x2 minus e to the power minus 2x2 minus x2 equal to 0. So now with this equation I can simplify it further. I can get 4x2 minus e to the power minus 3x2 equal to 0. Now this is a very nice looking nonlinear equation, and one could probably solve it using any numerical technique like the Newton-Raphson method and so on, and that's what I have done in my book. But today I'm going to solve it using a different method which is going to give me a closed form solution. So to do that, I'm going to use the Lambert W function. Now let us just replace that x2 by y so that we are simply looking at a typical nonlinear equation, and let's try to solve this. So I take this equation, I rewrite it as follows here, and then what I do is I bring the e minus 3y term to the left hand side. So I get 4y e to the power 3y equals to 1. Now I take this here and I rewrite in this form here, and once I rewrite it in this form here, I have multiplied both sides by 3 by 4. I essentially can write it in this manner. So what I did here is I got rid of these two 4's here. There was a cancellation, and I got it in the form 3y e to the power 3y is 3 by 4. Now the aim for doing all this manipulation is that I wanted to get this in a form which matches with the Lambert W function. Now remember the Lambert W function, when it works on something like a e to the power a, it gives me a. So now I have the left hand side in that format, so I apply the Lambert W function to both sides, and then the left hand side simply becomes 3y, and the right hand side becomes the Lambert W function of 3 by 4. So then I can immediately write y is 1/3 W3 by 4, and so this is a closed form solution of this particular equation here. Now the W3 by 4 comes out to 0.46915, and so the value of y is essentially 0.15638. Now how did I get this value? Again, I got it from the software, or rather I should say the online mathematical system known as Wolfram Alpha, and here I put Lambert W3 by 4 and I got this value here. Of course, I got a value to a huge number of decimal places, but I am satisfied with 5 decimal places, so I took 0.46915. So now we go back to our equation in terms of x2, and we know the solution of x2 is simply 0.15638. So I know x1 will be 2x2, and that's going to be 0.31277. That is simply twice of x2, and therefore I can write x star as the stationary point, which is given by 0.31277 and 0.15638. So this is the stationary point, and it's a stationary point of this particular function. Now the next question is this stationary point which we obtained in the previous question a minimum point? So let's try to show that. So what I do now is I take this function, I know its stationary point, and I calculate the H matrix. Now the calculation of this is given in optimization tutorial 1. You can check it out. You simply have to take the second derivatives and you will get this. Now once I have this, let me put this value of x star in this H matrix here. So we do that here and we see that there is a term e to the power minus x1 minus x2 in this H matrix. So we can calculate this particular term. It comes to 0.62553. I put it in the H matrix. I get H at x star is this particular value. So remember that in the sufficient condition, you have to actually calculate the Hessian matrix at the value of x corresponding to the stationary point, and that's what we have done here. Now we can find the eigenvalues of this matrix using our usual method, but here I just go to some online system and I get the values of lambda. They are 2.446, 4.805, and so both these values are positive. Therefore I have a positive definite Hessian matrix, and therefore this point x star here, the stationary point, is a minimum point. Now if you are wondering how I got the particular lambda values, I got it again using Wolfram alpha, and these are the two lambda values which have been given to me by the Wolfram alpha system. Let's now start looking at problems where some constraints are there, so we get closer to real life. Now this problem is pretty simple, but it can help us figure out certain important concepts in optimization. So we have to solve the optimization problem. Minimize the function fx is x1 square plus x2 square subject to x1 plus x2 equal to 1. So this problem, you can of course see it's a circle and a straight line. You can even solve this graphically, but we are going to solve this numerically today, or rather I should say analytically today. So let's take this problem here, and what we do is we construct something known as the Lagrange function or the Lagrangian, and this is given by L x v, and this is x1 square plus x2 square plus v into the constraint here. So the form of this Lagrange function is that it is the function f of x plus v into h of x, and that's what is done here. Now once I have this Lagrange function, I can think of this as a function of x1, x2 and v, and I can then set the gradient vector of this to 0. So that's what I have done here. I have taken dl by dx1, dl by dx2, dl by dv, and set this equal to 0. So you can see here differentiation is pretty simple. So the first term I get is 2x1 plus v is 0. The second term I get is 2x2 plus v is 0, and the third term I get is x1 plus x2 minus 1 equal to 0. So when I differentiate L with respect to V, it simply throws back the equality constraint at me. And now I can take these two equations and I can solve it. So for example, if I subtract these two equations, I will immediately get x1 equal to x2. Then I can substitute this x1 equal to x2 in the third equation. That's going to give me 2x1 equal 1, or x1 is half, which is again equal to x2 because of this condition here. And then I can also calculate the value of v. V is going to be minus 2x1. That's going to give me minus 2 into half, or minus 1. So these are of course the KKT conditions for the equality constraint problems. So those, if you do not remember, are the Karush-Kuhn-Tucker conditions. Again, refer to my lecture for clarity on those conditions where I have derived all the theory. Now, sometime you can solve this problem directly also. It's quite simple, but before we do that, let's just list the solution. So this is the problem: minimize this function subject to a certain constraint. We formed the Lagrangian and we got the solution here, and we also got the Lagrange multiplier. Now, we could solve this kind of simple problem by simply taking h of x, which is this value, and then expressing x2 in terms of x1. And that's what I've done here. I have written x2 as 1 minus x1, and then I have written the function f of x out. So f of x becomes x1 square plus x2 square, and this becomes x1 square plus 1 minus x1 square. So that I have got from this term here, x2 is 1 minus x1. Now I have a function which is simply in one variable x1, and therefore I can immediately set the derivative to 0 with respect to x1. So I get 2x1 plus 2 into 1 minus x1 into minus 1 equal to 0. Now I can immediately solve this system. So or this equation, I get 2x1 minus 2 into 1 minus x1 equal to 0, or 4x1 equal to 2, and that gives me x1 is half and x2 is half, which is the same solution which I obtained previously using the Lagrange function method. Now let's do the inequality constraint problem, which is somewhat more complex, and that problem is to minimize the function given here, and the constraint is x1 plus x2 greater than equal to 1. So now you remember, if I have any problem in this form, I can put it in standard form by actually changing this particular inequality into less than equal to form. So to do that, I take this particular term here or expression here, and then I multiply both sides by -1. So this is what I get, and then I can write g of x is minus x1 minus x2 plus 1 less than equal to 0. So once I have written g of x, the inequality constraint in this form, I can form the Lagrange function for this particular problem as x1 plus x2 square plus u into the constraint gx here. So what I have done here is I have put f of x plus u into g of x. And remember, I add this plus s square term, that's a slack variable. And when I add this, I essentially am converting the inequality constraint to an equality constraint. Now, when I form this kind of Lagrange function, there are two things I need to keep in mind. One is that s square should be always greater than equal to 0. That of course is coming by the fact that we have picked s square itself, and also u is greater than equal to 0. So the Lagrange multipliers for the inequality constraint should be greater than equal to 0. Now I get the 4 KKT conditions for this problem. That is, I differentiate L with respect to x1, x2, u and s, and set them equal to 0. So you can see here that this Lagrange function is a function of x1, x2, u and s. So I'm essentially treating this as a multivariate function of 4 variables. And with the gradient being set to 0, I get these 4 equations, and I can simplify it slightly more. So the first equation gives me 2x1 minus u equal to 0. The second equation is 2x2 minus u equal to 0. The third equation gives me minus x1 minus x2 plus 1 plus s square is 0. And then the last equation gives me us equal to 0. Now, this particular equation which you get in the case of the inequality constraints, this is also known as the switching condition. Now let us take these 4 equations, and we are going to look at the different cases which are possible with the switching condition us equal to 0. So I have written those 4 equations here, and we are going to consider these cases one by one. So the first case is u is 0. So if we put u is 0 in this system of equations, of course us 0 is satisfied, and the first equation is going to give me 2x1 equal to 0, so that will give me x1 equal to 0. Then I get to x2 equal to 0, which is going to give me x2 equal to 0. So you see what I did, I substituted u is 0 in this equation here. Now the next equation is going to become minus x1 minus x2 plus 1 plus s square equal to 0. But since x1 and x2 are 0, I'm going to get s square is -1. Now that's not possible by the fact that we have defined s square to be a positive number, and therefore this particular solution is ruled out. Now the next solution is s is 0. That also satisfies u s equal to 0. Now I put that into these three equations. I get 2x1 minus u is 0, 2x2 minus u is 0, and the third equation becomes minus x1 minus x2 plus 1 is 0. Now I can solve these equations. So let's say I subtract these two equations, the first and the second. I get x1 equal to x2. I put that in the third equation. I get minus 2x1 plus 1 equal to 0, or x1 is half. And then I use the fact that x1 equal to x2 to get x2 is half. So I have the solution here, x1 is half, x2 half. And what happens to u? U becomes 2x1 from this equation here. And so since x1 is half, u becomes 1, which is greater than equal to 0. So this set of variables or numbers I have given in green, this actually satisfies the requirements for this problem. And so this is certainly a valid feasible solution for this problem, that is x1 is half and x2 is half. And in this case what happens, because s is equal to 0, the inequality constraint is satisfied as an equality at the optimal point. Now we should also consider the third case, the possibility that u is 0 and s is 0. So in this case I make this substitution here. I get x1 x2 is 0 from the first two equations because u is 0, and then I put it in the third equation. But what happens in the third equation is that I would get something like 1 equals to 0, or in fact these two are 0, so you are getting something which is certainly not possible. So therefore this is a not possible condition, that 0 equals to 1. I think this should be 0 equal to 1, and this is of course not possible, and therefore this particular system is also not possible. So the only solution we are getting out of these three cases which are thrown by the switching condition are x1 star is half and x2 star is half, and that's the solution for this problem. So in today's tutorial, you learned several things. You learned about the necessary and sufficient condition for optimization, how to find the minimum points of a single variable function, of a two variable function. Now, once you know how to do these things for a two variable function, you can expand that concept to a three variable function, to a four variable function, to a n variable function, if you start thinking in terms of gradients and Hessian matrix. We also saw how the KKT conditions can be used to get the optimal points or the feasible points for a problem. And we also use the KKT conditions to get the minimum points of function with equality constraint and inequality constraint. Finally, take a look at optimization lecture 3 if you have not done so, to solidify your theory for the problem, and you will see the derivations of the necessary and sufficient conditions there. That is, why should the derivative be 0? Why should the second derivative be greater than 0? Why should the gradient be 0? Why should the H matrix be positive definite? All those are given in optimization lecture 3, and certainly make it a point to continue seeing my optimization playlist for the full course as I continue to release out these tutorials in the optimization class.